Dear ladies and gentlemen, good afternoon everyone and welcome to my presentation about modeling of an oscillating water column in DualSPHysics. First of all, thank you for joining this session. I am Nicolas Quartier, a PhD student at Kent University, and I will be talking about a type of wave energy converter, or WEC, called the oscillating water column, or an OWC, which is a WEC that uses the oscillation of the water surface inside a chamber to generate electricity. The arriving wave energy drives the oscillation, thereby compressing or decompressing the air above the water surface inside the chamber. This air is then driven through an air turbine, thus generating electricity. These OWCs can be floating or fixed, and in this research, the fixed oscillating water column is studied. Some examples of oscillating water columns installed in the past are the Limpet OWC in Scotland, the device at the Mutriku breakwater wave plant in Spain, the one at Civitavecchia in Italy, and one in Korea. In Korea, a fixed OWC has been installed before near the shore of the Jeju Island. In 2016, however, another OWC project was launched, this time with an OWC applicable to small breakwaters, and experimental tests with this OWC have already been performed in the ocean basin of the Korea Research Institute of Ships and Ocean Engineering, or KRISO. The experimental data provided by KRISO was used for a project initiated under the International Energy Agency, Ocean Energy Systems, called WEC Modeling, Verification and Validating. An overview of the experimental case is given here, and it's a scale model of the prototype with a scale of 1 to 4. So it's an oscillating water column which is fixed and has a sloped chamber with a small orifice at the top, which causes the PTO system damping, the power takeoff system damping. Selection is made from the experimental cases to simulate with DualSPHysics, as you can see from the table. Firstly, a numerical wave tank is modeled that is suitable for the scale of the tested wave conditions. Simulations are performed with and without power takeoff system, in 2D and in 3D. Without the PTO system, the orifice diameter equals the duct diameter. That's what we mean with 1.0D in the table here. With the PTO system, we mean that there is a damping effect on the free water surface inside the OWC chamber caused by the small orifice on top of the chamber that causes the compression and decompression of the air inside. Adding the air phase in DualSPHysics, however, would be computationally too expensive, so it was chosen to work differently. A thin plate is added floating on the free water surface with the PTO force acting on it. The question could be asked why to use SPH for this kind of problem, since mesh-based CFD like OpenFOAM can be more suitable for an OWC with modeling of the air phase as well. And that's in fact a good point. However, in SPH, you don't have issues with meshing. Plus, this case also provides validation for future cases in more extreme environments, such as for floating OWCs. In those cases, mesh-based CFD solver might not be ideal anymore. Floating OWCs have already been modeled in DualSPHysics, however not with the inclusion of a PTO system as is the case here. So it was first assumed that the air inside the OWC chamber is incompressible. There is a relationship between the pressure difference P and the airflow QW driven by the free water surface, which is given here in equation 1. Since the air is incompressible, it's assumed that the airflow driven by the free water surface is the same as the airflow going through the orifice. That's what expressed in equation 2 here, with S0 the area of the chamber and Z dot the heave velocity of the floating plate. Once the pressure difference P is known, the PTO force F acting on the floating plate can be calculated, and this force is then implemented in Project Chrono coupled to DualSPHysics. In the next stage, the air is assumed compressible. The same relationship between the pressure difference and airflow rate is valid. However, the airflow rate QP is no longer equal to the airflow driven by the free water surface, as was the case for incompressible air. Based on thermodynamic relationships and the assumption of air being an ideal gas, equation 4 can be formed, where it can now be seen that QP, so the airflow going through the orifice, depends on the derivative of the pressure as well. This derivative is simplified here in the current research and finally leads to a new expression for the airflow rate QP. The pressure calculated with QP is then checked with the experimental data of the pressure. And as can be seen in this figure on the right, it's clear that the formula and experiment fits well. Before starting simulations, a convergence test is performed, in this case for the undamped OWC. It's found that an interparticle distance of dp equal to h divided by 4, so 1/4 of the wave height, gives sufficiently accurate results without leading to excessive computational time. Thereafter, the results of a case with incompressible air are compared to the results obtained with the assumption of compressible air. It's found that the compressible air gave more accurate results without increasing computational time, so this formulation was used for all cases with a power takeoff system. Now, an overview of the obtained results will be displayed, starting off with the 2D results. For the cases without PTO system, so without a floating plate inside the oscillating water column chamber, the free water surface elevation was measured at 3 different locations inside the chamber. It's found that the numerical results agreed well with experimental results, especially at the center of the OWC, so that's the green line. Small disagreements are caused by the resolution or because of the use of 2D instead of 3D. After these simulations without PTO systems, and now simulations with PTO system are carried out. And you can see here how the PTO system is numerically implemented. A plate is floating on top of the free water surface and a PTO force is acting on it, represented by the white spring. The water surface elevation at the center of the OWC chamber is then computed as the heave of the plate, displayed in red. Also, the airflow speed through the orifice is calculated by calculating the airflow QW, and that's then displayed in blue. Both quantities are compared to experimental results and they seem to agree very well for this particular case at least. This simulation in 2D with the PTO system is carried out for 4 different cases. As can be seen, overall there is a good agreement. Again, small discrepancies can be due to the fact that we're simulating in 2D instead of 3D or because of the resolution. Next, a series of 3D simulations were performed. The dimensions of the numerical wave tank are equal to those in 2D. However, now periodic boundaries are added at the lateral sides, thereby cancelling the need for lateral walls and also avoiding the lateral reflection. The number of particles here is about 26 million and the runtime is more or less 6 days for 50 seconds of simulation time. Results of the free water surface elevation at the center of the OWC are displayed in red. The airflow speed is displayed in blue. When comparing these results with the 2D results, it was found that the error in amplitude and phase is lower. A general finding in these results is that the airflow speed obtained with DualSPHysics, so the blue dotted line, fits better with the experimental airflow speed for positive values than for negative values. This can be related to the fact that the experimental calibration constant used in the calculation of the airflow rate and the pressure is calibrated with the outflow only. So now some final conclusions and future work. As you could have seen, DualSPHysics is able to accurately model the water surface elevation inside the oscillating water column chamber and also to accurately model the airflow rate. Validation of a fixed oscillating water column is useful for floating OWCs in the future. The effect of the power takeoff system or the orifice damping can be implemented here in the project chronocoupling by adding a force on the plate floating on the free water surface inside the chamber. This has, however, the disadvantage that there's no variation possible in the water surface elevation along the width of the chamber. Now in the future, more 3D simulations will be carried out also with longer simulation time. Thank you for your attention, and if you have any questions, feel free to ask.